Okay, yeah, very good. Hold on. Glad I checked. Turn that off. Okay, here we go. So we've been dealing with ideal gases your whole chemistry career. Okay. Can you now tell me the definition of an ideal gas? Like, what is this, like textbook bullet points for an ideal gas? What is an ideal gas? Right? We always assume it's an ideal gas, but what is it? What does that mean? There's two things that...
1 atmosphere and 273.
Okay, you're talking about standard conditions, but what is the ideal gas? Like what, when we say water's behaving like an ideal gas in this situation, what are the properties of an ideal gas? What? Yeah, right.
It's got no volume, it's just a point.
There you go. Okay, point masses, no volume. So the mass is in a single point in space. Okay, so the volume doesn't take up any volume of the container in the room. Like if you put more gas in the container, there should be less container volume, right? And so for an ideal gas, there's no detectable volume. So we could say that if it's behaving like an ideal gas, it's got no volume to the particles. Okay, and another way to say that is a point mass. So the only way they can collide is if they actually try to occupy the same point in space. So it's very easy to detect collisions because only when x equals x and y equals y is there a collision, because there's no radius of the particle. So that's one of the parts of the definitions. The other part is there's no attractions and no repulsions, no intermolecular forces. They're going so fast that they bounce off, and they're elastic collisions. And so that's like billiard balls, right? There's really no detectable attraction or repulsion of the billiard balls. Wouldn't that be funny if there was slow speed attractions? Like if they're going fast, you can play billiards, but if they're going slow, they're attracted to each other. It'd be no fun. It'd be hard as heck to break. You're there all touching, bam, and the whole triangle goes against the wall. You know? So it'd be really bad. Terrible pool. Terrible. But you can do that with magnetic balls. That would really. Anyway. So that's what we mean by ideal gases. So what do real gases have? Well, they have volume and they have attractions, repulsions. So we'll explore that. To bring up James's point, we have standard conditions that go with these things. And so we have SATP and STP. We talked about these earlier. I want to kind of go fast through some of this like vocabulary stuff. So STP and SATP are different. So just make sure that you pay attention to that. And this is where we get a good, sort of written down definition of what a bar is and what an atmosphere is. They're both written in terms of pascals, which is a Newton per square meter. Okay. And what is a Newton? Remember your physics formula. Newtons of force, F equals ma, so a kilogram a meter per second squared. Okay, so that's what a Newton is. And then the volume, the molar volume, so the volume of 1 mole of a substance at SATP is 24.789 liters per mole. At STP, it's 22.4. So if you have that memorized from freshman chemistry, that 1 mole takes up 22.4, you've got to remember that that's at STP. So don't fall into that. If you make a conversion using that remembered molar value, that's not the volume of 1 mole at SATP. Since we're at a higher temperature, the volume is larger, so it's 24 liters per mole, not 22. Now we get into gas mixtures. I just want to review Dalton's Law. So the pressure exerted by a mixture of gases is the sum of the partial pressures of the gases. So when we get into the mixing gases, not in the next couple of sets of notes, but probably three lectures from now, we're going to have this combination phase diagram where we have the mole fraction of a substance. So this would be the mole fraction of B. So that's moles of B over moles of total. Okay. And so if those are equal, we have 1. So all the way to the right is all B, and all the way to the left is all A. And the total pressure is just the sum of those two partial pressures. So here the partial pressure of B is that mole fraction times the pure vapor pressure of B. And so there we have it. So that's Raoult's law. This X diagram essentially is Raoult's law. So let's jump in and talk about this ideal gas idea. This ideal gas, they have no attraction, infinitely hard collisions. They're point masses, so they have no volume. And so when they collide, this is what happens. There's no potential energy difference. As they come close together, there's no change in potential energy. And then they hit each other, and there's an infinite jump. So they can't go into each other, so they hit each other, so they're really hard collisions, and they bounce off. But there's no drag when they leave. There's no acceleration when they come together. There's nothing like that. But a real gas, as you might imagine, have some attraction and softer collisions. So they squish, and they have a radius. So this would be the radius of the particle. So we're talking generally. It could be an atom, it could be a molecule. And so there's a contact point. So this is when they sort of, whatever you want to define as the electron cloud boundary, there's a collision, and the potential energy goes positive there. So there's a repulsion. When the potential energy is negative, again, they could go to negative or lower energy, so there's attraction. And so as they're coming in, you start to see dispersion forces, dispersion, dipole, and hydrogen bonding. So all of these intermolecular attractions start to draw the molecules or atoms together. They reach a minimum, which would be the radius of attraction, and their optimum distance, and then they would collide, and there would be this repulsive area. So if they're going fast enough, let's say they come in with a velocity that gives them this much energy right here. Okay, so they go they sort of roll in through the attractive area, and they hit, and they get to this point, so that they finally stop when the potential energy matches their incoming velocity. So all that kinetic energy is turned into potential energy, and they stop. And now we're above that 0 point, and so they're going to roll back out. So you can just think of this as a ball. If they come in with a ball with this much kinetic energy, that ball is going to roll down this hill and up to here and stop, and then it's going to roll right back out, and there won't be any condensation. But if you cool the molecules down, and where's the best place to cool them? At the walls, right? Because you sink the heat away. Then those molecules at the walls are cold. Something comes along, hits them, and then molecules dislodge. And so you have a really cold molecule with low energy, and another molecule comes in and hits it, and they kind of come to equilibrium, and now that ball loses some energy, and it's down in that well, and so then you have a condensation. And so with this real gases, we can have condensation because of this region here. This region here allows for condensation. And that condensation could be in the form of a liquid, or it could be a solid. It could adhere like deposition, like freezer burn. If you put your stuff in the freezer, there's a partial pressure of water in the freezer, and it goes from water subliming, goes to gas phase water molecule, and comes over here and builds a nice, beautiful crystal of ice on something else. And so it's going from gas straight to solid. That's condensation too. So the whole physics area of this is called condensed matter. So it could be solids, it could be liquids. We typically think of condensation as liquids because we drink iced tea, but in the freezer it happens too. Okay. And I typically call it deposition to distinguish between liquid and solid. So let's talk now about some of the ideal gas law properties. And you've seen these curves before. Saw them on the last test. Okay. So PV equals a constant for ideal gases, and these constant curves are called isotherms. If the volume goes up, the pressure goes down. And so we've seen these isotherms. So if you take two of these isotherms and you connect them with adiabats, we have the Carnot cycle. So the adiabats go like this. And you have A, B, C, D. So these isotherms, they don't intersect. The adiabats don't intersect, but they can intersect each other, the adiabats and the isotherms. And that's where you get these heat engines. And that's what we're using in these different gas properties to create these spontaneous circles that produce work and take in heat. And so let's take this case, one of these isotherms, and try to figure out what happens if this condenses to a liquid. So let's use this one here. So what happens if at this volume we start to condense to a liquid? So right here, we're at this volume. We're following this isotherm in. We're squeezing it, right? So we're compressing it. We get to a point where all of a sudden a liquid starts to form. What is the volume of a liquid compared to the volume of a gas? So our x-axis is liquid, or our x-axis is volume, sorry. So where would I draw the volume of the liquid? Just think about it. If you've got a liquid, you put it in a closed container. Let's say you close the lid all the way down to where there's only liquid in there, and you start to heat it up. What's going to be? If the container's closed, sealed, what's going to happen? Boom, it's going to blow up. Why? Because the volume of the gas is much larger than the volume of a liquid. So we're cooling a gas, it starts to condense. So what happens? Where's the liquid volume on this scale? It's going to be way down here somewhere. So let's just pick right here. So this will be the volume of a liquid. And we have gas and liquid in equilibrium. And we have that vapor pressure of the liquid. And there'll be a line drawn straight across. So notice how if we squeeze the container, let's say we have this in a piston, we squeeze the gas, the pressure's going up, we're sinking the heat because of it's an isotherm. And then we get to the point where a drop of liquid starts to form inside our piston. All right. Now when we squeeze the gas, the pressure doesn't go up anymore. What happens? Yeah, the drop of liquid grows. So we're squeezing on the gas, but it doesn't push back anymore. We're just sort of squeezing the gas into that liquid droplet. And the liquid droplet starts to grow. Okay, and that's the vapor pressure of the liquid. So it's just the constant pressure. So that's a straight pressure across. And what we're doing when we're moving the piston over here is we're just changing the proportion of gas to liquid. So we start out where it's all gas and one drop of liquid. And then we get down here and it's all liquid, one little bubble of gas. And if we keep squeezing, that last little bubble of gas will become liquid and we will have no vapor volume in their piston at all. It will be right at the volume of the liquid at that temperature. What happens if we continue to squeeze? Eventually, yeah. But the liquid is going to be compressible, barely, a little bit compressible, but its isotherm is going to be much steeper because if you try to squeeze on a liquid, it's going to push back. And so that's the isothermal compressibility of the liquid. And it's much steeper than the gas. So the gas's compressibility was much more shallow. You squeeze a lot and the pressure goes up a little. The liquid, you squeeze a little, the pressure goes up a lot. And then eventually up here, you would hit the solid liquid equilibrium, where you keep pressing on the liquid, but a tiny little crystal of solid has started to grow. And now you're just pushing that liquid into the solid. And then you hit the point where it's all solid in your piston, and then the compressibility of the solid is even more steep. And so you're just squishing that solid, and you're now pushing the molecules closer together. They will squish a little bit, and the bigger the electron cloud, the more squishy they are. But you just push down. So this is what an isotherm looks like in a real gas situation. We come along, we press on the gas, the pressure goes up, then we start forming a liquid. We have this equilibrium zone. Then we push on the liquid, it goes up, and then we have a liquid-solid equilibrium zone. And then we push on the solid. And there may be other solids, like a rearrangement of the crystals, like from T-shape to square rhombus to tetrahedral. So we could do those things too in the solid, and we might have solid phase equilibria as we go up in pressure. We're talking about hundreds of thousands, maybe millions of atmospheres pressure, okay, which would be relevant in, the core of the Earth or something like that. So that's what we have here in this phase diagram. So as we look at this thing, now this one's for water. So when you're looking at it from this direction, you're looking at this picture here on the right. Okay. So you're seeing the isotherms here, and you're seeing this liquid solid equilibrium region. So I'll pass this around a little show and tell. Now this one has a strange feature. The liquid solid equilibrium is sort of an inner ledge, and that's water. It's really weird. Water is so weird. Okay, it's got this inner ledge where the solid is, the volume of the solid is larger than the volume of the liquid, right? It expands when it freezes. Whereas all the other substances I've ever come in contact with, the solid is smaller than the liquid. The solid is more dense than the liquid. Water, the liquid is less dense than the water. The solid is less dense than the liquid. The solid floats. All other substances, the solids sink. They're more dense than the liquid. We wouldn't be alive if that wasn't the case. That's where weathering of rocks and all that stuff, the splitting of rocks, water gets in there, freezes, breaks the rocks apart, and all that thing. The life in the lakes and rivers when they freeze up or down below that ice. If the rivers froze from the bottom up, all the fish would be exposed and die. So it'd be easy fishing for the early winter, but there wouldn't be any fish left after that, at least far enough for. But anyway, it's pretty neat. I'll pass that around. Your lab this week is on this PV phase diagram with condensation. And so we'll talk about it a little bit today. So here's carbon dioxide's actual phase diagram. It's got a lot of things going on here. You see the different isotherms. They're labeled 243, 258, and so on. And this yellow region is that region of liquid and gas equilibrium. So this is a PV phase diagram. The PV diagram we've been using this whole time for our engines. Way out here in the gas phase, we have our adiabats, and we have the A, B, C, D. So there's our heat engines out here where we're dealing with gases. We start to push those gases. Sometimes if we're below the critical temperature, then we have the possibility of condensation. If we're above that critical temperature, we don't have the possibility of condensation. Okay. So that's when we talk about critical temperature, critical pressure, critical volume. There's all three right here. Okay, so that's the critical point. Now look at the difference between the ideal gas and the real gas. So here's the isotherm assuming an ideal gas, and here's the isotherm using a real gas. And let's just pick, here's a good spot right here. So this says 120 is the predicted pressure, and the actual pressure is around 80. Okay, so 80 is 2 times 40, and add 40 to 80, you get 120. So that's 50% error. Right? If the actual is 80 and you predict 120, you're 50% high. That's pretty bad error at this volume, at this really small volume. So we've compressed that gas down and we're off by 50% in our predicted pressure. But look out here. Look at the error out here. It's not that much. So at really large volumes and low pressures, that's our ideal gas region. And so that's what we have way out here. These are isotherms. This is the volume. of the gas at 258. This is the volume of the liquid at 258. So when we're in this region, let's just say we're right here in the middle. So let's take this this spot right here, that piston. We'll draw a little piston here. And we've got liquid and gas. And this is telling us sort of how many moles of liquid we have and how many moles of gas. So we've got about half and half. Half the moles are in the liquid phase, half the moles are in the gas phase. And the liquid phase is a smaller volume, so it's a smaller spot in that piston. Okay. And then way out here to the right is the gas region. Here, that blue region is all liquid, no meniscus. Okay. Notice this region has a meniscus. That's one way to tell where you are in a phase diagram. Do I have gas and liquid in equilibrium? If I have a meniscus, then I can get gas and liquid to go back and forth. Make sense? I've got gas and liquid in equilibrium if I have a meniscus. Okay? Or if I have a solid, I've got an interface, a gas-solid interface. But over here in this liquid area, the liquid is completely filled the plunger, the piston. So I can't change, there's no gas in there. It's all liquid. Whereas over here, gas is all gas in the plunger. So no meniscus in this region here. So this region here also, no meniscus. The only place you'll find a meniscus is when you have the gas-liquid equilibrium. And then this up here is a supercritical fluid, and it's above the critical point. So that's the super part. It's not supercritical like it insults you or anything. It's just, that's my joke. Thank you. She's my buddy. And so it's the density of a liquid, but it flows like a gas. Now, how do gases fill containers, right? They fill all of the spots of the container, whereas a liquid is governed by gravity. And so in this case, we have the density of a liquid, but it flows like a gas, meaning it fills the whole volume. And that's where we do supercritical fluid extraction, supercritical fluid chromatography. We use supercritical CO2 for a lot of things. That's how we decaffeinate beans, coffee beans, is that we put the coffee beans in a container and we pump in CO2 and keep pumping until it's supercritical, and it behaves like a solvent. It's great. And so it dissolves the caffeine out of the beans, and then we just pump that CO2 over to someplace else, pop the pressure, and the caffeine just drops out, and the CO2 is recycled. And it's a great way to just extract things, because you just pop the pressure, and all of a sudden your liquid phase, it's really a supercritical fluid phase, goes to a gas, and whatever was dissolved in that just drops right out. And you can keep it really pure. These critical constants are interesting, above which no liquid phase can exist. So there's no meniscus above this, and there's no liquid phase. But you can get a high density out of a supercritical fluid and do things like extraction with it. Okay. Now here are the critical constants of several gases. And so you can see the hydrogen, helium, and so on. Helium looks like it's got the lowest ones here. So, 2 atmospheres, 58 mils per mole, and then a 5 Kelvin. So you're not going to get liquid helium above 5 Kelvin. Okay, but you get below 5 Kelvin, and you could get liquid helium if your pressure was lower than 2, and you had a volume that was, comparable to 58 mils per mole. You get up to water. Now we're dealing with some high temperatures. So you have no hope of getting liquid water above 650 Kelvin, okay, because you're above the critical temperature. So you can kind of use these critical temperatures as a gauge to the properties of gases. And then we can talk about compression factor, where we determine the intermolecular attractions of their various substances. So This is an interesting calculation, right? For an ideal gas, look at what we've got. PV equals nRT. So for an ideal gas, Z is 1 because we have no intermolecular attractions, okay? But if you were to put in a certain number of moles of gas in a particular volume at a given temperature and measure the pressure, okay? Notice I've told you the moles, I've told you the temperature, I've told you the volume. You should be able to calculate the pressure. Well, yeah, you can for an ideal gas, but what's the actual pressure? See, so since the actual pressure isn't your ideal gas pressure, then you can calculate Z. And sometimes that pressure is higher than you predict, okay? And sometimes it's lower. So up here, when it's higher than you predict, like in these cases here, repulsions dominate. And doesn't that make sense for hydrogen? H2, you got 2 protons that are not even in the same nucleus. They're out and about. And you've got only 2 electrons shielding those 2 protons. So hydrogen hates other hydrogen. It's just awful. And when we talk about a hydrogen economy, no. I mean, they try to compress hydrogen. This tells you it's worse than an ideal gas. That an ideal gas would give you less pressure in a container than hydrogen would. Hydrogen would give you more pressure. It's fighting you the whole time. Yeah. If you get a Z lower than the ideal, then its attractions are dominating. So that's pretty cool. And you can see a larger molecule like methane or ethane would have more attractions. And look at ammonia, it hydrogen bonds. And so it's like, I mean, eventually I think it might come back up. You put it at a high enough pressure or small enough volume or something that it'll come up where repulsions, dominate. But yeah, that hydrogen bonding, it's really easy to compress ammonia. So the ammonia economy, you learn terms of running around with tanks of ammonia. Yeah, you bet. I can carry a lot of ammonia. I can carry more ammonia than I can carry hydrogen. And so this is pretty cool. That boil temperature, I just put that in there because it's not the boiling temperature or the boiling point. It's the boil temperature. And it's the perfect temperature that you would have where this region is 1 for the longest period of time. And so if you're at the boil temperature, you have the best possibility of that gas behaving ideally. That's all there is. This is kind of just a trivia thing, really. So the gas behaves perfectly over a wider range of conditions than at other temperatures. Okay, I kind of ran through that so I could get to this corresponding state stuff because this is crazy. Okay, so we have this compression factor, right? It's basically treating everything. I mean, every gas has different critical constants, right? And water's critical temperature was 647, and helium was 5 or something like that. And there's this principle of corresponding states. Now, I could just see some engineer thinking, what if we divided everything by their critical constants? So I took the temperature of water and divided by its critical temperature, and I took the temperature of ammonia and divided it by its critical temperature. Could these equations, could the behavior of the gases be the same if I just scaled everything by its critical temperatures? And the answer is yes. Okay, so if we take this pressure and the actual pressure of the gas, we take the actual pressure of the gas here and we divide it by its critical pressure, and the actual volume divided by critical volume, actual temperature divided by critical temperature, we end up with these reduced variables. That's what R stands for, reduced variables. Engineers call these unitless pressure, unitless temperature, and unitless volume, which I heard that once and I was like, you engineers have lost your minds. What is unitless temperature? That, right? That's bad, right? I hear that and I'm like, what are you talking about? And it's because they're dividing by a standard state, right? This critical state is what they're dividing by. So anytime you hear something crazy like unitless variables, you're talking to an engineer and you need to ask them, what state are you dividing by? You're scaling it by something, okay? And we've been using this in chemistry. We have unitless concentration in our equilibrium constants. we just never tell you because a freshman would freak out over that. But we take the pressure over the standard pressure, which is typically 1 atmosphere. And so our pressures are unitless, and our concentration divided by our standard concentration, which is typically 1 molar. And so all our concentration units disappear in those equilibrium constants. Why? Because they're actual approximations to the partition function. And our partition functions are unitless. So anyway, it's a sort of a side trip. So let's look at what happens when we use the reduced variable comparison. Here's the Z, here's the compression factor. Okay. Remember, 1 is an ideal gas, so it comes straight across here. And then we've got these curves. And so this is temperature over to critical temperature. So here we're at a temperature that's 2 times the critical temperature. Here, 1.2 times the critical temperature. Here, 1. So this is right at the critical temperature. And we have all of these dots with different squares and circles and so on. And then we come look at those. So obviously a bunch of different data falls on the same lines. That's nice. Let's look at the legend. Nitrogen, methane, propane, ethene, really different molecules, all behaving the same way. Isn't that cool? That means I can make this graph right here, and it'll be the graph for almost all the gases. And then if I want to know how water behaves in this, I just need to know what the critical temperature, pressure, and volume for water are. And then I can take whatever my current temperature for water is, divide it by its critical temperature, and then I can find it on this plot, and I could then learn what the actual pressure would be at that temperature and volume and number of moles. So this is a great engineering tool, is to be able to generate these charts that reflect the behavior of a bunch of different kinds of substances. Once you find that factor that you can divide by and create a reduced variable, then you can use these charts and cover a large amount of materials. So it's just mainly, I've introduced this, I get so excited about it because this course is kind of the exit ramp for engineering. And so I'm trying to sort of give you some insights into what engineers do and how they approach problems. And if you really like that, then you might consider going into engineering, after your undergrad degree. A friend of mine, he got his master's in engineering. He got a chemistry degree, but he liked PChem too. And he was like, I kind of actually like engineering. And so he went and got a master's in engineering. He had to take a couple of undergraduate courses to beef him up in terms of engineering. It's what they call STEM work, so he could actually be successful at the master's level. But it was a good path for him. He ended up going into civil engineering. He's been working in Austin for 20 years as a civil engineer, so he's doing great. So here's just some calculations talking about hexane. At 1 atmosphere and room temperature, what temperature would we have to have H2 at to behave like hexane? So what are our hexane's reduced variables? Well, at 1 atmosphere, if we divide it by its critical pressure at 30 atmospheres, it's 0.03. So it's 3% of its critical pressure. And the temperature is about 60% of its critical temperature. So it would behave, hydrogen, according to these engineering principles, would behave like hexane if it were at 3% of its critical temperature and at 60% of its critical temperature. So we could say, what pressure of hydrogen would we need? Okay, if its critical pressure was 13 atmospheres, we would need hydrogen at 0.3 atmospheres, and the temperature, the critical temperature is 33, and if hexane behaves the way we like pouring it into our gas tank at 60 at 60% of its critical temperature, 60% of hydrogen's critical temperature is 60% of 33 Kelvin. So we'd have to be at 19.4 Kelvin. But for your energy QSPR, if hydrogen was your fuel and you wanted it to flow like hexane, you'd have to be at half an atmosphere and 19 Kelvin. But said you could put the thing into the tank and pour it just like you pour hexane, because it would have that kind of property. Yeah. Okay. So probably not realistic. Okay, we've got a few more minutes, and let's get into this lab. So this is what y'all are going to be doing this week in lab. You may have heard the van der Waals equation, because they were saying, well, that obviously we calculated that we were 50% error with ideal versus actual for CO2 at that particular volume. And so this van der Waals equation, let me get the, he added two terms. So here's the pressure, right? And you might say, well, what is the pressure? Pressure is nRT over V, right? So here's the ideal gas law right here. Ideal gas law, IGL, okay. And that was our first equation of state. You put in the state variables and you can calculate the pressure. Okay, and so he added two terms. He said, well, the volume is going to be decreased if I have a volume element here, right? So that the molecules actually take up space, then I need to decrease the volume of the container. If I decrease the volume of the container, the pressure is going to go up, right? So taking up space in the room, again, the molecules have less room to go in, and so the pressure should go up if the molecules take up space. But if the molecules have attractions, then I need to add an attraction piece here. So this is the attraction piece. So that's going to reduce the pressure. And so this van der Waals equation is what's being plotted here. There is a problem with the van der Waals equation, though. It does this little loopy thing, okay, which is not realistic. So let's just sort of stand here on the curve in this unrealistic region of the van der Waals equation, okay? And so I'm right here at this pressure, and I squeeze the container, so I make the volume smaller, and the pressure drops. Not realistic. Okay, so that does not happen, no, okay. Or I release the, I try to give the molecules more space, and the pressure goes up, no. Okay, so this behavior is not real. But that's what this equation gives. So the van der Waals equation was actually supposed to correct this area here. It's good, okay? So it corrects the gaseous behavior. It's dealing with gases. It tries to give a more realistic pressure for the gases. But when you get close to condensation regions, it's not good. So Maxwell came along and said, what if we draw a line here? So this is Maxwell. He said, let's draw a line through this loopy region, which is loopy, and let's equal the lower area and the upper area. So let's just draw a line here, because that does give us the behavior of condensation. Remember I said you reach the condensation point and it goes straight across, and that would then give us the vapor pressure of the liquid. Okay, so that's the Maxwell construction. You draw that line so that this area, the yellow area, is equal. Okay, and that's what y'all will be doing in the lab. So y'all have the van der Waals equation. You look up a molecule, you get the A and B terms, you put that in the equation, you calculate your pressure. You get this curve. And then you find a vapor pressure where the area above that line and the area below that line eventually are equal, and you use solver. So you move that pressure line up and down until your integral goes to 0, or however you want to set up the problem. Y'all are going to be given a little more freedom in this spreadsheet, okay? So use your critical thinking skills and find that vapor pressure. That's the vapor pressure at that temperature. Write it down over here. Make it a new table over here. Temperature, pressure, okay, for that substance. Then change the temperature, which is going to change the curve, which means you need a new vapor pressure. So you do solver again and get a new vapor pressure. So then you make another temperature pressure pair. Okay, do that 5 times for several gases. And then you get to do this right here, the Clausius-Clapeyron equation. Notice it has the vapor pressures, how vapor pressure changes with temperature. Kind of a crazy equation. It's 1 over temperature, okay, over here. And you have the enthalpy of vaporization. Let's see, do I have that written down? No, I don't. Enthalpy of vaporization. That's how many joules it takes to vaporize a mole of substance, okay? And then you have the pressure pairs. This is an amazing equation. I'm shocked that a simple equation like this works so well. Look at this vapor pressure, the R, the gas constant, times the natural log of the pressures of water, vapor pressures of water, divided by the triple point. Look how linear that is. And that goes over this range all the way up to the critical point. So that tells me the vapor pressures from 273 Kelvin all the way to 600 and almost 650 Kelvin. That's incredible. And all I need to know is any one of these pairs. And I know this one. I know the boiling point of water. So that's my star. This is 373.15 and 1 atmosphere. I just need to know those 2 points and the vaporization enthalpy of water, and I can tell you the vapor pressure at any point from the triple point to the critical point. That's amazing, and it's a pretty simple equation. This is the one equation I used after graduation. Like, I remember thinking I learned all of those things, and I got into industry, and they were asking me to do calculations, and this was the one. I used this one the most. Schrdinger equation, even though I love it, never used it. Symmetry, mainly just seeing bridges and stuff. Oh, yeah, C2, you know. But this one, my job, I needed this one for my job, calculating vapor pressure. Because they wanted to know if a tube of glue totally evaporated, would the vapor pressure reach the point where the guys working on the nuclear weapon would pass out? Right? Important calculation. Schrodinger equation? Yeah. I mean, never mind that all of nature is based on Schrodinger equation, but you don't actually have to calculate it. But this one, yeah, you will use this one. So we have a lab on it. So y'all pay attention.